Thank you for the introduction. It's also a pleasure to be here, so thank you to the organisers. So I'm going to do something a little bit different in this talk, in that I'm going to try and get across the idea of a proof. This is something I don't perhaps normally do, but I'm also going to give you a flavour of impossibility results as well in Koopman operators. So our goal will be to classify when we can and cannot learn spectral properties of Koopman operators. This is based on this preprint here with Igor Mezik and Alexei Stepanenko, which will appear on the archive this evening. If you're super impatient, you can also look at my webpage as well. Okay, so, I can do this manually. There we go. Okay, so the objects in this talk, we have a compact metric space. This is the state space. We have a state that lives inside this state space, and there's a continuous function that governs the dynamics. Okay, so the state at time n+1 is f of the state at time n, so a discrete time dynamical system. So this is really sort of the 19th century geometric viewpoint. Moving into the 20th century, we have the Koopman operator. So we have a Borel measure omega on x, which allows us to define a function space, so functions that are L2 integrable with respect to omega. Elements of this space are called observables. We've already seen the Koopman operator in a couple of talks, but here it is again. So the Koopman operator is this composition operator here. Okay, so it's a linear operator, whether or not this f is linear or nonlinear. A slight sort of comment, you have to be very careful about defining this in a pointwise sense on what really is a space of equivalence classes of functions. There's some sort of fine print here for those of you who care about those kinds of details. Okay, so that's 20th century. Moving into the 21st century, what we now have is, instead of knowing f, we have an unknown f, or it might be too complicated to study analytically. And available to us is a collection of what's called snapshots. So these are just data pairs, x and y, where y is f of x. Okay, so one time step forward of x. These could come from a single long trajectory, for example, if you have an ergodic system on an attractor or something like that, or multiple shorter trajectories, experiments, numerical simulations, whatever. I'm not really going to specify that until later. Okay, so this is the Koopman operator. And a lot of the effort in this Koopman community is to try and learn spectral properties of this operator. Remember, it's linear, from this data. Okay, so when I first got into Koopman, I decided to plot a graph. I've probably shown this to lots of you in the audience before, but there's really this exponential increase in papers on Koopman operators over the last decade or so, a lot of them applications of Koopman operators. There's a few surveys as well, so there's a 2012 one, Applied Koopmanism, 2022 one, and Sign Review. I've recently done a 2024 one on sort of the multiverse of dynamic mode decomposition algorithms, so trying to get a handle on sort of the vast array of all of these different methods that compute different things. Okay, so there's all of this stuff going on, but at the moment there's really an open question that hasn't been addressed yet, which is, when can we learn spectral properties of Koopman operators from trajectory data, and when can we not? So this part in particular is perhaps difficult to answer. Okay, so the goal of this talk is to try and go some way to answering this question, and to present to you a classification tool that allows you to, well, answer this question, but also do things like prove that your algorithms are optimal. Okay? So this will have 4 parts. I'm first going to go through an impossibility theorem, which you can think of as constructing an adversarial dynamical system that tricks your Koopman algorithm into not converging. The second part, a possibility theorem, I'm going to introduce something called towers of algorithms. And this will allow us to compute things. So a bit mysterious, the name, but it will become clear as we go along. Impossibility and possibility, once you've got these two combined, you can start to classify problems. Classify how difficult they are, classify your algorithms, and figure out whether they're optimal. And to do this, we're going to use something called the solvability complexity index hierarchy. And then I'm going to end with just some comments on sort of where this leaves us, where this branch of research is going. Okay, so let's start off with the impossibility theorem. We're going to launch straight in. So D here is the unit disk. I'm going to consider a class of dynamical systems. Okay, these will be dynamical systems where the F is continuous, measure preserving, and invertible. These induce unitary Koopman operators, so the spectrum's a subset of the circle. And I'm going to give my algorithms every possible chance of succeeding. Okay, and this will make my impossibility results stronger. So I'm going to assume my algorithm can access this data here. So any x in the disk, any ym, which is 2 to the minus m close to f of x. So it can sample f anywhere in the disk to any accuracy that it wants. And there are two statements. The first is that there does not exist any sequence of deterministic algorithms, gamma n, that use this data and converge to the spectrum of the Koopman operator for all f in this class. Okay? Now you might ask, what if I have things like Monte Carlo sampling, stuff like that? Well, if you allow random algorithms and take any sequence of those, the probability of success is bounded above by 1/2. Okay, so you can do no better than coin flipping, random chance. This is a universal impossibility result. It encompasses any type of algorithm. Okay, so it's not just, DMD or neural networks or anything like that, anything. Okay, and also any model of computation. So this means that even if you could do real number arithmetic on a computer without round off, you still can't get past these impossibility results. The phase transition here at half is optimal. There's some interesting maths behind that I won't go into. Notice that this is a very nice class of dynamical systems. We can learn statistics, okay, from this data, and that doesn't help us. I'm going to show you it for the disk, but the proof idea extends to other state spaces as well. Okay, so this is saying we can't construct a sequence of algorithms that converges. So let's go through the proof idea in the deterministic case. So the idea is to start off with f0, which will be rotation by pi. Okay, so I'm going to use polar coordinates. It's quite straightforward to show that the spectrum of the Koopman operator associated with f0 is plus or minus 1. You can do that via the Laplacian eigenfunctions on the disk. And the mechanism that allows me to sort of embed complexity into my dynamical system is this phase transition lemma, okay, which is based on some work in this paper here. So what it's doing is it's saying that I can construct, given data, a measure preserving homeomorphism that makes me conjugate with f0. So specifically, think of these as snapshot data, x points, y points, distinct points strictly inside the disk or some annulus inside the disk, which have anti-intersection. Then there exists a measure preserving homeomorphism h, such that h acts on the identity of this annulus. And if you take x, apply h, then rotate, you get back h of y. Okay, so you get this conjugacy. So the idea will be to use this lemma to trick a supposedly existing algorithm into not converging. Okay, so here's a very rough sketch of the proof. We're going to do it via induction. So we're going to suppose for contradiction that gamma n, a sequence of algorithms, uses this training data and converges to the spectrum. I'm going to define an adversarial f, okay, that will screw up the convergence. So I start off with a slight perturbation of rotation by pi, calling it f1 tilde. So I've got a bump function here. So this is the dynamical system. So you rotate by pi, and then if you're inside radial coordinates here, you have this bump function. Okay, you can show that the spectrum of the associated Koopman operator is an entire unit circle, using separation of variables, for example. Because we assumed convergence, there exists some n1, some integer n1, so that the output of the algorithm is close to I, right? I being inside the spectrum. So I'm going to assume that it's 1 close. Okay? But when the algorithm spits out its answer, it's only been able to read a finite amount of information here, right? So that's the only assumption I'm making about my algorithms. Now I'm going to let x and y correspond to the snapshots, the data that it's seen when it spits out this answer. And then going to apply the lemma, okay, with these x and y's. And I'm going to define f1 to be this map here, which is conjugate to this rotation. The key point is, if I, at the risk of, so the key point is we've got this relationship here, which means that f1 and f1 tilde agree on this snapshot data. Okay? Consistent data is it's a deterministic algorithm. It has to behave in the same way, so it has to output the same set. In particular, we get this relation here. Okay, now we're in business. Because the spectrum of this Koopman operator is the same as the spectrum of the Koopman operator associated with f0, which is plus or minus 1. Okay, so we've got something that's looking like it's close to I, when actually it should be converging to plus or minus 1. So our goal is going to be to continue doing this inductively to define a sequence going to infinity where this relationship always holds, and a suitable f as a limit of these functions, and we get a contradiction. Okay, so here we go. We're going to repeat on different annuli that contract to 0. Okay, so we're always going to have this relationship here. Fk is conjugate to f0. Remember, these h act as the identity of the annulus. Okay, so we can glue them together. So we can take f to be the limit of these fk's. Consistent data means that the outputs are the same. In particular, we always get this relationship here. Okay, that for a sequence going to infinity, the output is close to I, but the spectrum of this is the same as the spectrum of the Koopman operator associated with f0, which is plus or minus 1. Therefore, we cannot converge. So here's the idea, right? You keep on doing these snapshot-preserving homeomorphisms, and you contract. Okay, so there's a bit of geometry going on as well. Okay, so let's just sort of step back a little bit. What have we shown? There's no sequence of algorithms that can compute the spectrum of Koopman operators, even with unlimited data and accuracy, of measure-preserving continuous systems on the disk. Okay, here's a possibility theorem. So this is sort of going the other way. So theorem B. So I'm now going to generalize to my compact space, and not just the disk, but this of course includes the disk, and consider continuous measure-preserving transformations. Same assumptions on the measurement device. Now there does exist a deterministic array of algorithms. So notice two parameters, n2 and n1, that's very important, that use this input data so that in the double limit, okay, so you take n1 to infinity, then n2 to infinity, you recover the spectrum for all f in your class. Okay, so really note this double limit. Okay, so this isn't contradicting the previous theorem, because the previous theorem was about a single limit, a sequence of algorithms. Okay, so this is very natural. For example, if you're applying DMD methods, your first limit might be taking data, the amount of data to infinity. The second might be taking the size of a dictionary or a matrix approximation to infinity. Slight caveat, DMD doesn't always converge. So we're going to fix that in the next slide. So here's the proof sketch. So we're going to apply a double limit, number of snapshots to infinity, then the size of a dictionary to infinity, to compute a function rather than a spectrum, a function of z, which is this reciprocal of the resolvent norm of the Koopman operator. So those of you who've done pseudospectra will recognize this immediately. Pseudospectra is simply the level sets of this function. Measure-preserving systems are very nice. Even if they're not unitary, you still have this relationship. Okay, so this function is actually equal to the distance of z to the spectrum. So in a double limit, we can tell how far a candidate z is from the spectrum. Turns out you can do an n-adaptive minimization of this approximation over a grid to approximate the spectrum. Okay, so you've got a two-limit approach. Here it is in action for undamped and damped Duffing oscillator. Okay, so the color shows contours of this pseudospectra. The blue dots are the EDMD eigenvalues, and you get a lot of spurious eigenvalues. I haven't gone through it, but you can actually use this relationship here to get error bounds on your output. And using this, we can see that the algorithm converges, whereas EDMD does not. This system, of course, is not measure preserving, but there are generalizations of this relationship for certain dynamical systems that you can use instead. Okay, so we have a two-limit approach that can compute the spectrum. We also have an impossibility result saying we can't do it in one limit. So now we can start to talk about sort of the framework and sort of the building blocks behind these ideas. Okay, so towers of algorithms. So suppose you have an array of algorithms depending on k parameters, n1 to nk, so that if you take k successive limits, n1 to infinity, n2, and so on, you converge to the answer. Then we call this array a tower of algorithms. Okay, and it actually is quite an old idea in dynamical systems theory. So we're definitely not the first to do this. So Steve Smale asked the following problem about finding zeros of polynomials. Is there any purely iterative convergent rational map for polynomial zero finding? So the problem being that things like Newton's method don't necessarily converge for cubic polynomials. Okay, so there's some very interesting dynamical systems theory about iterations of rational maps going on here. Kurt McMillan showed that you can actually devise a scheme for the cubic that replaces Newton's method, but you can't for higher degree. But he also showed that in the case of quartic and quintic, you can solve it using towers of algorithms. In this case, rational maps where you take iterations successively to infinity. Okay, so you can't do it in one limit, but you can do it in a finite number of limits. Okay, and then he solved that you can't, it showed that you can't do it for degree 6, even if you allow an unbounded number of limits. Okay, so this idea is very natural in dynamical systems theory. So we can start to talk about the structure of this. So this is where the solvability complexity index comes in, or SCI. This is simply the fewest number of limits needed to solve a problem. So for example, we blasted through two theorems. Theorem A, this impossibility result, was telling us that we can't do it in one limit. So the SCI is strictly greater than 1. Theorem B was showing that we can fix DMD to converge, playing around with those functions, okay? But we had to do it in two limits. So the SCI is upper bounded by 2. So you combine these lower bounds and these upper bounds, and you get that the SCI is equal to 2. Okay, so you've got sort of a number that tells you how complicated this problem is in some sense. Now, so far, the Koopman literature is really focused on theorems that are of type B, okay, so upper bounds, on the SCI. And these upper bounds need not be sharp, okay, so because we have a lower bound here that goes hand in hand with this theorem, we know that this is sharp. So for example, here's a table of some of the main DMD algorithms, okay, that computes various spectral properties of Koopman operators under different assumptions. Here's the upper bounds that you can read off from the theorems in those papers. Okay, so upper bounds on the SCI for the Koopman mode decomposition. So think of this as computing the functional calculus. The spectrum, spectral measures, spectral type. I'm not really going to go into those if you don't know what spectral type is, but think of it as like point spectra, so eigenvalues or continuous spectrum. Okay, and you can see that the upper bounds vary a lot. So for example, here we've got something that's 5, right? It's a very large number of limits that you have to juggle. Okay, this also appears in Ulam's method for transfer operators. Computation of SRB measures. So there you might have, say, a third limit as well as data and dictionary corresponding to smoothing. Okay, so there's a lot of methods that do that kind of thing. It also appears in control. So it's everywhere. Okay, this multiple limit phenomenon. Okay, so now we can start to talk about classes of computational problems, classifications. So delta 1 will be problems that can be solved in one limit with a rate of convergence or error control. Delta m plus 1 are problems with SCI bounded above by m. So the plus 1 here is historical and a bit unfortunate, but it's there to stay on. Okay, so this just tells you how many limits you need to compute something. We can refine this a little bit. For example, we might want to know whether the output of our algorithm is trustworthy. So sigma m are problems with SCI bounded above by m, where the final limit converges from below. So what do I mean by that? That's a kind of an obvious statement if you're converging in, say, R or a totally ordered set. But if you're talking about compact sets of the plane, complex plane, what you have to do is say that the output is contained in the spectrum up to some controllable error. Okay? So your algorithm spits out an approximation of the Koopman spectrum, and you know that everything in the output is 2 to the minus n accurate, for example. You can, by the way, replace this 2 to the minus n with any sequence going to 0. It doesn't change the classes. There's a dual notion, pi m, where you converge from above in the final limit. So if you're doing it in one limit, this would be that your algorithm up to this ball contains the spectrum. Okay, so you've got trustworthy output, you've got covers of the spectrum, which might also contain too much, but eventually converge. So these are sort of dual notions of verification. Okay, so you have these classes. We can now start to place different types of dynamical systems with and different objects that we want to compute, different spectral properties of the Koopman operator, into this hierarchy. So for example, oh, the color has, never mind, but this is SCI for Koopman 1, okay, the first plot I'm going to show you. So here I've got different classes of operators, different classes of dynamical systems, or F. So omega x will just be continuous systems. Omega m, I add the assumption of measure preserving. Omega alpha, I drop the assumption of measure preserving and replace it with a uniform modulus of continuity on F. So this is just telling me that I can control the variation of F. So the Koopman operators associated with this class can be horribly non-normal. So here we have our theorem A plus theorem B. It's sigma 2. Okay, so we converge in two limits, verification on the final limit. Here we have what happens when we have uniform modulus of continuity. So I haven't gone through the proof, but it's non-normality that really makes it require two limits. You can't do it in one limit. So all of these classifications are sharp. Completely general systems require three limits. Okay, so they're really hard. And to prove this result, you end up having to embed some combinatorial problems into the dynamics. It's quite a fun proof. You can also mix and match. So what happens if you take the intersection? You drop down to sigma 1. So you can do it in one limit with error control. Okay? Finite state space is kind of trivial. So that's where omega is x rather is a finite set. Okay, you can also do this for spectral type. Okay, so here you've got different classifications for different problems. We've got some pictures here of the type of dynamical systems that might have this type of behavior. So rather than going through spectral type, let me just give you one example theorem associated with sigma 2. So theorem C, take the class of smooth measure-preserving systems on a torus, okay? Then learning non-trivial eigenfunctions or even determining whether there exist any, okay? So whether the system is weakly mixing or not, has SCI equal to 2, even if you can sample derivatives. Okay, so it's very difficult. And this is sort of wrapped up with the whole problem of trying to find finite dimensional coordinate systems and embeddings in which the dynamics are linear, right? You're searching for these non-trivial eigenfunctions. Oh, I forgot to say, the trivial here corresponds to constant functions. So constant constant function is always, because we're on a compact metric space, always an eigenfunction of the Koopman operator, but of course it contains no dynamical information. Okay, so we can start to classify spectral type and all these types of things as well. Right, so to wrap up, where does this leave us? So we now have tools for lower bounds or impossibility results for Koopman learning. So I gave you one example of the flavor of proof. Many problems necessarily require multiple limits. Okay? You combine lower bounds with upper bounds, which are where you construct algorithms, and what this allows you to do is classify the difficulty of problems and prove optimality of your algorithms. Okay, so you can have a stamp of approval on your algorithm saying, I can't do it in less parameters. There's no clever rejuggling or parameterization or anything like that. This is optimal. We combined ergodic approximation theory and computational analysis to start to map out this terrain. So I showed you those two pictures of all the different classifications. This is only just the start. Okay, there's so many open questions. To make you remember this talk, turns out Buzz Lightyear was right? If you've seen Toy Story, to infinity and beyond, but I'm not sure whether he knew about the SCI hierarchy. Perhaps he did. Okay, so you have to go to infinity multiple times. Future work, other function spaces. So we saw this in Eagle's talk. Okay, impossibility theorems can also be proved in other function spaces. Partial observations, okay, what happens if you change the measurement device? Continuous time, control and other uses of Koopman operators. And beyond Koopman, okay, so you saw how we were sort of embedding sort of complexity into the system to trick an algorithm. This technique could be applied to other algorithms or other methodologies or setups used to study dynamical systems from trajectory data beyond just Koopman. So I'll end on a positive note. So where does your method fit into this hierarchy? Okay, and also, can you prove that it's optimal? All right, thank you.